Okay, so we're going to get started. Great. All right, so welcome to the 6th Compass lecture of the semester. Today our speaker is, oh, am I muted? Right, good. All right, so our speaker today is Julia DeMarines. She's an astrobiologist and science educator. She is currently a graduate student in UC Berkeley's Earth and Planetary Science Department. Her research involves biosignature and technosignature detections, the ethics behind messaging extraterrestrials, and the impact of educational activities. She holds a master's degree in space science, space studies from the International Space University, and a bachelor's in astronomy from the University of Colorado. Outside of academia, Julia runs her own outreach events called Space in Your Face, with the goal to communicate complex space concepts in fun and engaging ways, because everyone deserves to understand the universe we belong to. She's currently affiliated with the Ad Astra Academy, an organization dedicated to promoting STEM education amongst other under-resourced students worldwide, where she designs and implements curricula for K through 12 students with a focus on promoting scientific literacy and critical thinking skills. When she's not doing science and communication, she can be found cracking Uranus jokes, trying not to kill her plants, trail running, mountain biking, and hanging out with her sassy cat, Bella. Let's give a warm welcome to our speaker, Julia.
All right. Hi, everyone. I don't know why the video is not working, but you can just imagine what I look like. And it's probably underwhelming. So hold on. Hide floating meeting controls. Okay. Hopefully everyone can hear me. I'll just get started. So today I'm going to talk about what is Earth's technosignature, assessing what we sound like to perhaps an alien observer looking at our planet. I'm going to dive in a little bit to my background and journey to get to Berkeley grad school, and then kind of launch into the presentation. And I might go pretty fast over some stuff. So if there's any questions from the audience throughout, feel free to ask during, and same for all you all in the room. Great. All right, so I guess I'll start with I hate talking about my background because I was just lamenting earlier that I don't like, it sounds a lot fancier than it is, but I am a National Geographic Explorer and have been a National Geographic Grosvenor Teacher Fellow and have won a grant from Nat Geo to do an education project in Nigeria, and currently amongst 4 other people, a California National Geographic chapter leader, where we create events to engage the public with all of the wonderful things National Geographic California explorers are up to. And in some of my existence, I've gotten to do some really cool things. One of them was being a science blogger on the research vessel, the Atlantis, which looked at some hydrothermal sea vents in this really deep part of the Caribbean, where they didn't think hydrothermal sea vents would even exist at all. So that was really cool. Also lived for 2 months on this drilling vessel that was drilling underneath the seafloor, looking for juvenile continental crust formation. And got to pretend that I was living on Mars for 2 weeks at the Mars Desert Research Station, which is actually in Utah and not on Mars, even though it looks like Mars. And that was also a really fun and unique experience. And got to fulfill a childhood dream of working with the SETI program here at Berkeley, with the Breakthrough Listen Lab and the UC Berkeley SETI Research Center. All right, so just a little bit more about my background. I like to call it a perseverance of curiosity because I've had a kind of non-traditional academic career and non-academic career. After about 15 years of astrobiology research, exploration, and education, plus 5 years of graduate school, the most impactful concept I've learned is pedagogy, which is the method and practice of teaching. And I'll talk a little bit more why that's like my buzzword today before we get into the science. But yeah, let's take a step back in time and I'll let you know how I got kind of into the sciences. Here's a picture of some of my family members. On the left here is me being a little punk. I'm probably 8. This is my older sister and my dad. This was taken from an old slide deck, so I'm sorry if my mom's on here and she's mad that she's not on that picture. But my elementary school was a public elementary school, and we had a teeny tiny planetarium we must have had a killer PTA, but we had a teeny tiny planetarium. And so from the age of 5, living next to a big city of Washington, DC, I got to see what stars could look like from this tiny planetarium, and it blew my mind. And when I was 13, my dad rented me on VHS, if you all remember those, the movie Contact. And that really inspired me to get into the field of astronomy and astrobiology. I did my undergraduate at University of Colorado at Boulder in astronomy and a little bit of geology as well. And then got a master's degree at the International Space University in France. Then I moved to California, got into Berkeley, and started during the pandemic. And everything was on Zoom. And about a year and a half into that, I learned I was neurodivergent. So this is kind of me coming out as being neurodivergent. I didn't really identify or understand what that meant. And so I just want to give a shout out to those who do experience a disability like neurodivergence, because it's not a normal or easy path, and it comes with a lot of challenges that aren't present for neurotypicals. And that's something I've really struggled with, especially over the pandemic. All right, so that's the cliff notes of who I am. But jumping into this science here of assessing Earth's technosignature, the motivation is to answer the question, how detectable are we? So currently, technosignature searches like SETI are the only available tool to unequivocally detect life in the universe. And I'll talk a little bit more about what that is and why that is in just a moment. I can go into this if you'd like, and I'm just going to decide that we are, because I can't see who's responding in the chat. But Earth is our only data point for life as we know it, both biologically and technologically. So it's a good place to start. Of course, this doesn't encompass everything that could be out there that is a sign of life. But in the search for technosignatures, we're looking for signs of advanced or intelligent life. And if you look at some of the images down here, the one on the lower left is the ozone hole, the hole in the ozone layer caused by CFCs, which is a pretty complex molecule that is man-made. And nature really wouldn't just make CFCs, no matter how much primordial soup you zapped in a vial. We have signs of physical technosignatures, such as the Voyager golden records here, like this record here, or the Pioneer plaques. Technosignatures could also be physical in the form of, like, say, a Dyson sphere, or these swarms of sort of satellites that are reflecting energy from a distant star back to its planet to gain energy. And we can search for these using optical and radio telescopes, as well as other parts of the spectrum. So yeah, in this project, we aim to empirically detect ourselves using the moon as a natural reflector of radio light. And I'm going to dive a little bit into this question. If anyone's familiar with astrobiology, there's a lot of folks out there looking for biosignatures. And it's a very hard thing to do, especially if you want to look at it remotely on, say, an exoplanet in the exoplanetary atmosphere. So in our atmosphere, we have very, very simple molecules. We have oxygen and H2O, CO2. One of the kind of buzzwords in astrobiology is looking for an exoplanetary atmosphere that has methane and oxygen at the same time, because they would normally react and reduce. But the problem with these atmospheric biosignatures, these simple molecules, is that they're not complex. They're ubiquitous throughout the universe. They're everywhere. So we can't really say with current technology that we can unequivocally detect life on another planet using just atmospheric biosignatures. I'm going to jump into a friend's research. This is a paper from Dr. Sarah Walker and Dr. Lee Cronin of the Arizona State University and of University of Glasgow. This is one of their students. They do this really cool thing for life detection that I think is going to be the way to empirically and unequivocally detect life out there. That is a little bit more, that is more definitive than looking for these ambiguous biosignatures. So their method is using this theory called assembly theory. You can think of these blocks on here on the left as Legos. So you can think of, you have a red block, you take one step to add a blue block, you take another step to add another set of those, you take another step to make it bigger and bigger, and then you have this little square donut of Legos. And this is a pretty complex structure. When I talk about complexity, the cell phone that people on Zoom can't see me holding up, this is probably one of the most complex things in this room, or the computer here. No matter how much you spark primordial gas, you'll never randomly get out a cell phone. So a measure of complexity is a good sign of looking for of life. So you can think of each of these steps here in this molecule building as a chemical reaction, going bigger and bigger and bigger molecules. And once you get to a really large molecule, some of these over a certain number of steps, basically, or levels of complexity, it just doesn't exist without life making it. So I'm going to zoom in to this graph here. I don't mean to confuse it with all these plots, but here is the, they call this a measure of assembly index on the left. So this is how many steps you would need to create these molecules. And I'm going to zoom in to this bottom left here. So when you look at all of these molecules that are produced in the kind of salmon color, these are all inorganic molecules. In the red, which is probably hard to see, are abiotic molecules, or abiotically made. Green is biological. Blue is this basically things that are dead. And you can see that all of these other colors they end at around 15. So this is the basically complexity of 15, the least amount of pathways you can get to make these molecules. So any molecule that has a complexity over 15 is only made from life, of course, as we know it. Yeah.
What is abiotic?
Produced by something non-living. Yeah, thanks. So I didn't mean to confuse everyone with biology. I'm not a biologist, so don't at me with questions about this, but I just think this is a really cool way to do that. The problem with some of these larger molecules is that they are in small abundances and they might not exist in enough density to detect them, say, in an exoplanetary atmosphere. This might be only possible for, say, in situ detection, such as like a Mars sample return. Speaking of Mars, there is a instrument on the Mars Perseverance rover that is trying to detect lipids, which is the kind of casing of cells, basically, which are used in all biological processes. However, you can make lipids. They're pretty simple. They're not very complex. So this wouldn't be an unequivocal life detection, even detecting these lipids. So it's a good step in the right direction, but perhaps we need to wait to get these samples back to really say if there was once life or is life on Mars, or if it's just a hellhole. All right, so back to radio astronomy. The big questions is, what is Earth's technosignature in these radio frequencies, and how has it changed over time? Why is this important? Why do we care? We might be at a turning point. We might be at this moment in the human civilization where we are becoming either radio louder or radio quieter. In 1995, we shifted from analog to digital signals, and I'll go into a little bit more about that. And now we're using fiber optics quite a bit, which don't produce radio emissions. So our technosignature is changing all the time. And it's important to know how our only example of an intelligent communicating civilization changes its technosignature over time. Perhaps we might find that we are in this going to a radio quiet place in our civilization, our history, that we might want to focus more on looking for these CFCs, these complex molecules in exoplanetary atmospheres, or in situ on some of our other worlds in our solar system. So I think I just basically said all of that. Yeah, so talking about radio waves, you probably are all familiar with AM and FM radios and radio signals. And I just kind of wanted to show a visual of how, like, AM is amplitude modulated. So you actually modulate the height of the amplitude of your wave, whereas FM is frequency modulated, and you're changing the frequency to convey information. In 1995, I was mentioning this earlier. I don't know if anyone was alive to remember those commercials, like, get your digital TV box today. And we switched from these more powerful analog signals to these digital signals, which require less power to convey the same amount, if not more, information, and they don't degrade as much as analog signals do over time. So we're transmitting, we can transmit the same amount of information, but using less power. And when we're thinking about an onlooker, the more power you give a signal, the farther it can be detected. So that's why this is important, this shift. So I haven't defined technosignatures yet, but I'll do that right now. It's a detectable signature of extraterrestrial technology or intelligence. Actually, we'll leave it as technology. I don't want to get into an intelligence debate. So when you hear the word moonbounce, I don't know if this is an East Coast thing, but we'll get to this in just a second. I got ahead of myself. Most radio waves penetrate through the atmosphere, except for very high frequencies. They can get bounced off. In fact, that's one of the ways we did long distance communication, and we still do. We bounce radio waves off the atmosphere, ionosphere. We could do this by sending a space-based telescope to spy on ourselves, but that's very expensive. And we have this beautiful moon that is a natural reflector of radio light. It's not perfect. It's kind of like a dirty mirror, and it reflects only about 7% of radio light. So yeah, I don't know if you call these moon bounces, but I grew up calling these moon bounces or bouncy castles. But this always comes to mind when I talk about Moonbounce. But really what I mean is we have a transmitter on an antenna on one side of the Earth that's going to give off a signal, is going to be bounced off the moon or reflected, and hopefully be received by our antenna that is looking, our radio telescope that is looking at the moon. Here's a visual, very not to scale, of how this looks. We are most likely going to be getting signals from the limbs of the Earth as from the vantage point of the moon. And I'll give a visual in just a moment of how that actually looks and works. And we're trying to detect only signals that are being reflected or bounced off the moon. And we don't want to get any of these local radio frequency interferences, we call that RFI, into our telescope. The reason why is very faint signals anywhere nearby the telescope could get into the telescope what we call side lobes or minor lobes here. So this is kind of what a radio telescope sees. It has this main lobe where it's very sensitive, and it has these side lobes that you can get signals in that aren't what you're really looking for. So in all radio astronomy, we have to be careful of this sort of noise that's coming in from nearby. All right, so basically we don't want to pick up these things. And there's a few tricks to being able to get at only the reflected stuff. So where in the radio frequency spectrum are we looking? This is impossible to read, so I'm not expecting anyone to read this, but this is basically how all of our radio spectrum is split up and divided. You're going from 0 kilohertz and all the way up to over 30 gigahertz. I actually cut off the bottom frequency there. But this looks to me more like some abstract art piece. But this is how currently we divide up our radio spectrum. You can think of the analog as like a rainbow, like who gets to transmit on the color blue, who gets to transmit on red. But you can see we're divvying up all of these frequencies. So it's very, very noisy right now. A lot of people gunning for these more and more divided frequency spaces. So we are looking, ooh, I got ahead of myself once more. There are folks who have done a similar experiment, specifically Woody Sullivan, and a paper titled Lunar Reflections of Terrestrial Radio Leakage, which was based off of lunar reflections made in the late 70s, early 80s. And these other two were using arrays. So we're using a single dish telescope like Sullivan et al. Did. So we'll kind of ignore these bottom two for now. All right, so they looked, and we are looking in this part of the radio frequency. And just to give you an idea, the blue that I'm kind of pointing out here is TV broadcasts. All right, so here are those previous studies and what part of the frequency they actually observed. And some of the results from those earlier studies were able to very clearly see TV stations that were broadcast from Eastern Europe, and literally they figured out it was Channel 8. And I thought that's pretty cool. And some of the most powerful transmitters that were discovered were actually ballistic missile surveillance from a surveillance radar in Texas, which was actually not on the limb. And I'll go into that in just a second. So we should expect to see a pretty high signal of 10 to the 5th Jansky's return signal using the telescope that we are using, which is the Green Bank telescope. So we have a sort of baseline of what we should be able to detect from our typical cell phone towers. And I'll kind of go over these later on. But a way to get at like what's actually being reflected is looking for signals that are actually shifting. You might remember Doppler shift. Everyone, I don't know, maybe you can poll the online community. Does everyone know what a Doppler shift is? You know, when the like ambulance goes by you and it's like, wah, 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 that sort of thing. I can't see anyone's faces, so I don't know if this is landing at all. I do have a demo. I don't think it goes well over Zoom, but should I do it? All right. I don't know if Zoom will be able to pick this up, but here I'll describe it for those who can't see me. It's a styrofoam ball on a string that has a annoying kind of buzzer sound. And I'm gonna just whip it around my head really quick. Ready? Right, okay. I think I got those parts from like the last Radio Shack that ever existed. I don't know if it picked up on Zoom. I've tried this once on Zoom and like, I think it like filtered out the sound as background noise, but hopefully you heard the change in pitch, and that basically happens with light as you have a moving object giving off radiation, any type of wave going towards or away from you. So to model this, to understand how much shift we should expect, We made some assumptions just to kind of get an idea of how much shift we should expect. And these are the assumptions, which the moon is not in an equatorial orbit. The Earth is not a sphere. The Earth-Moon distance is not fixed, but yeah, we use those to kind of just make a back of the envelope calculation. So here's the Earth, and you, the viewers, are going to be the moon. And if a signal is coming at you from the left hemisphere of the Earth, it's going to be blue shifted at you because that side of the Earth is like approaching you. It's less distance once you get to the middle here from where the signal is being transmitted to where you are, if that makes sense. And it would be red shifted or lower pitches in the sound analogy if the transmitter is going away from you. And you have to think about it not only going to the moon, but coming back from the moon. So you could even get a double blue shift or a combination of these two, depending on where your transmitters are and where the radio telescope is. So we wanted to kind of model this to understand how much shifting could possibly happen. And I'll just highlight this orange curve here. This is showing the amount of megahertz that it would be shifting from an initial frequency of 800 megahertz. So it's a very, very tiny amount. If you think of your FM radio, this would be like even less than changing it from 99.5 to 99.51. So very, very, very tiny shifts. And then we know that those shifts are going to be changing because the Earth is rotating on a sphere, and to take the change of that Doppler shift, we call this the Doppler drift. And to understand that, we have the Earth rotating and giving those signals going to the moon, returning back from the moon, back to Earth. And then we have to take into consideration the orbital speed of the moon. And so this really ugly and boring plot here is showing the maximum drift rate one could expect to find. And this is in hertz per second. So very, very tiny from the lower wave frequencies all the way up to the higher one. So very, very small. All right, so where are transmitters located? I'm gonna check the time. All right, I'm gonna try and go fast here. They're all over the place. We don't have all of the data of known transmitters. We're just not privy to some of transmitters, say in Asia and Russia. But we were able to model what we knew. And so all of these red dots are known transmitters that are very powerful. So we kind of took off some of the lesser powerful transmitters. And we expect to see transmitters from the limbs of the Earth, and what I've highlighted here. So to do a sort of analogy of this, here you can imagine that this moon here, pretend it's the sun, and everything in this swath here is going to be daytime, and everything outside of it is going to be nighttime. So from the perspective of the moon, if you're an astronaut looking at Earth, you would be seeing all of this stuff within this kind of curve here. And so this is actually what we call the sublunar point here where the moon is. And we have highlighted transmitters that we would expect to find at the limbs at this specific observation time. All right, so let's talk about the observations. We've observed 40 hours on the Green Bank telescope, which is the world's largest steerable structure. It's about 100 meters in diameter, and I think the area of over 3 football fields. Is that right? Getting some, yeah, okay. There's some radio astronomers in the audience here, so just confirming, make sure I don't put my foot in my mouth. Yeah. And we have 30 minutes on the Parkes telescope, which is located in Australia. And I forgot to mention the Green Bank telescope is in West Virginia. So we have 40 hours over 8 nights. And we are adding to this radio frequency space in the red here and in the red here. And then in the Parkes observations, that 30-minute one, it covers this area of the radio spectrum. All right. And because of those lobes that I mentioned, try and do this slide quickly. Basically, depending on what frequency you're observing at, you're going to see a certain sort of beam width or area of the sky, and which is outlined in the blue for the lower frequencies and red in the higher frequencies. And in order to make sure we're not getting any sort of gunk from reflected off of the moon in our off observations, we need to point very far away from the moon in our off observation. So I probably didn't mention this, but we're doing 5 minutes on the moon, 5 minutes off the moon, and in that cadence for as long as we have our observing night for. So the kind of goal here is to be 3 what we call beam widths away. So we're making sure not to get any sort of reflection from the moon in our offs or off observations. So the first 3 observations were kind of garbage. They were not the required number of bandwidths away. But our first observation is on night number 4. That was pretty good. And then jumped to analyzing the data of observation number 6, which has a very far separation of our on and our off. The first, trying to calibrate this 4th night of observations turned out to be a living nightmare, and I think I was losing hair over it. So once I switched to the higher frequencies here, it was like chef's kiss, butter, super good. Okay, so taking a look at our first clean observation, we're looking at this part of the radio spectrum. So we've got things like TV broadcasting, mobile phones, amateur radio, which is cool, and things of this nature transmitting in this space. And a tiny little sliver for radio astronomy here. Let us have some, right? What we record, we have 3 data products that we get at various resolutions. And I'm going to kind of skip over this. But if you're interested, there's a paper that describes basically what we call our back end that was written by Lebowski et al. And the rest of the Breakthrough Listen team that I recommend checking out. And what's happening to these signals? Here's a schematic of what's going on. I feel like Dave will appreciate this. So here's our telescope. We're measuring in the 800 frequency range. What we're receiving are kind of like whispers from space. So we got to amplify it. And we've got to basically use what we call mixers to convert it into frequencies that we can actually measure. Some of the frequencies are just way too fast. We can't basically take samples fast enough to record that. We use an analog to digital converter and basically do a Fourier transform to store it on our computers, at which we analyze later on. Is that good, guys? All right. So wanted to show you kind of like what we're seeing. So here's what the frequency space we're looking at. Here's our first on-moon observation of 5 minutes. Our time is going up, so it's a 5-minute observation in seconds, and the colors represent the power, which is arbitrary because it's not calibrated yet. But what I wanted to point out in this image here is that our on observation is much more powerful than our off observation, which is pointing away from the moon. But you might notice there's still some power being received. There's still some flux density coming in that we need to figure out how to remove from both of these. So this is why we do an on and an off to make our calibration and kind of clean our data. So preliminary results, we can use this awesome program called TurboSeti to set our limits, our drift rates, our signal to noise ratio, and just kind of want to show you a snippet of how this works. And in this first observation with these kind of parameters, which I've changed more recently, we've found 449 hits of things that have been most likely reflected. And wanted to show you, maybe just focus on the frequency plot on the right. We've had a high signal to noise ratio in a few of these. So I'm going to be looking at some of these higher signal to noise ratios. Looking at all of these hits on the right here, there's quite some large signal to noise ratio in around 735 megahertz. And I looked up because if you remember, the swath was going through kind of the east coast of America. And I was like, okay, it looks like it's going through near where I grew up, near Washington, DC. And we know there's cell phone towers being transmitted. And I was just poked around and found out that T-Mobile transmits in these areas. And I was like, maybe I was looking at a text message from my mom or something. So I just kind of got excited. Looking at a visual of our hits here, here's our on observation compared with our first off, and going back on and off and on. If those signals were in a very straight line, we would likely believe that they came from something fixed to the telescope. So it's not being reflected off the moon. What is showing here in the diagonal is our signal of interest, what we would call a hit, that's being kind of fitted by this red line. So we're looking for things that have this, what we call drift here. And here's just another signal, another hit in that range. So there's a lot of calibration. I'm going to skip over this because it's a lot to talk about in a very short amount of time. And if you want to talk about it later, feel free to email me. But basically, we have to get rid of the influence from not only our internal telescope noise, we can refer to that as gain, and we have to get rid of the Milky Way background radiation at the exact location of our observation, as well as the cosmic microwave background radiation. So a lot of gunk that we have to kind of clear up and figure out how to remove. So here's our first kind of calibrated data. It's pretty high power, some of these spikes here. And we're gonna kind of zoom into those areas of interest that I was mentioning before with the high signal to noise ratio. And here they are. Don't get too excited, but this was pretty exciting for me. This is in our low resolution data, so they would be a little bit more pronounced in our high resolution data, but these are much faster to run through our calibration. So I'm pretty psyched on these two little blips here. And yeah, so it's kind of what we're looking at. And once we get kind of a database on kind of the average, sort of we understand what we're seeing in these swaths that we're observing at, we can paint a much better picture of the power being emitted from Earth. And that will be able, then we'll be able to directly compare to what it was back in the earlier observations that I mentioned. So the current status of this project, this is a lot of words to throw at you, but basically was able to make a program that's able to run many of our files. Remember, we have 40 hours of data to make it like very fast. There's a word I'm looking for that I can't place on my tongue. Efficient, I think. Anyone? I don't know. Tip of the tongue. So yeah, basically making an algorithm that we can run through a lot of this data much more quickly at these 3 on-off pair cadences, and be able to find these hits and examine them. And future work, want to keep doing this and make sure our calibration is sound. I have a few questions about the power and want to make sure those are actually accurate. And then once we kind of get a sense of what we're seeing in over one night of observation and over all the nights of observation, whatever data that was good, we can extrapolate across the globe perhaps, and then be able to sort of understand what the power is and understand what our technosignature is and how that might be perceived by an onlooker. So I don't have any exciting definitive results for you today, but I wanted to share the process of this I think very exciting research. And then from that, we can see how far those signals could actually be observed at various distances with like different telescopes. All right, so thank you very much. Hopefully I didn't go over time. And if you have any questions, I welcome them at this point. And sorry again, you can't see me. Yeah, thank you. Yes.
Just a clarification. You send signal on the moon, or you just look at whatever.
Yeah.
Back from
Exactly. Yeah, we're looking at the question was, are we sending signals to then observe? No, we haven't, but there are amateur radio astronomers who do this EME, it's called Earth Moon Earth communication. So it would be really cool to see if there's maybe opportunity for a future observation to observe one of those campaigns. But right now we're just looking at the kind of cacophony that already exists. We're not inserting any known signal. But that's a good idea. Yeah.
The only question from Zoom was, I think from your mom, Jane, asking why she was muted.
Oh, no. I knew it. I'm sorry, Mom. It was I put in that photo like 5 minutes before, and I'm sorry I couldn't find another one. But you're here in my heart, which is all that matters. Well, got called out for sure. Yes.
So you did a search using Turbo Study, which is a narrowband signal search, a drifting narrowband signal search. Are there any plans to try and search for signals that are a bit wider? And which leads to the question: might you consider trying to demodulate, decode the data that you have, try to pick up an FM station?
Yeah, okay. So the question was, are we the signals that we are using that we can detect that kind of we can comb out of our data using Turbo SETI algorithms are very narrow band. And the question from the audience was, are we ever going to do more broadband? And I would say we have all the data. So if there are any broadband algorithms that SETI uses, we can certainly apply that. I just haven't done it myself. Yeah, and then your second question, remind me.
Oh, kind of links to it, but trying to demodulate, decode.
Oh yeah, okay. The second question was, could we ever like demodulate or decode some of these signals to get the data out of it? So if we're seeing like a TV broadcast, could we like replay it? I really want to do this. I've heard it's challenging, but I think there's someone, it was recommended to get in touch with someone who I now forget who has done stuff like this. But there's a wonderful artist. Her name is Daniela De Paulus, and she's done these Moonbounce, this sort of artist campaign where she'll transmit a photograph and it will be reflected off the moon and received, and she will display what the kind of garbled image is received, so you can see how much the moon is scattering. So stuff like that has happened. I would love to be able to like decode some of this and hear if we catch a FM station or whatever, maybe, you know, spy on Russia low-key. It's fine. Just kidding, I'm not doing that. Please don't report me. Yeah.
The two spectra. Why? Yes. Why do we care knowing what exactly it is? If it's a cosmic wave background or something else? You could just use it as an imprint and you know, subtract it from the other.
Okay, so the question, if I'm understanding, is can you say it again, maybe?
Yes. I suggested that we can just take the Earth-Moon imprint and subtract it on the Earth-Moon. See what comes.
Yeah.
And you don't even need to study what the source is from this background.
So the question was, which is a good question, why can't we just subtract what the off moon is from the on moon? And one of the reasons we can't just point blank do that, the way this normal, I would say, I don't know if I want to say normal, we usually use a sort of calibrator, like a local oscillator, a known frequency that we can understand, kind of have it as like the control. If anyone's into spectroscopy, kind of like you have like a neon light that you gauge your other frequencies to, so you know kind of how your electronics are garbling, or what the noise is there. So you could definitely do kind of back of the envelope calculate just to get signal to noise by subtracting them. But I'm going to go back a few slides. And when our beam width is, say, this larger one, you're not getting just moon's stuff. You're getting all of this extra donut stuff from space, right? And that's going to be, this donut stuff is going to be different than this stuff over here. So these are different parts of the sky. It's mainly for calibration, and we're using the moon as our calibrator. And so we need to know all these details to get to actually put numbers, so it's not arbitrary units, to be able to say this is, whatever, 1,000 Janskis that we're seeing the signal at, to make it more precise in that way. Yeah. Does that make sense? Hopefully I answered that right. Any other questions?
There are no other questions. Let's take our speaker one last time.
Thank you. Cool. Sorry, Mom.